whole process. So now let's go to case study number 2, which we're going to calculate, but I'm going to ask you to do the analysis. Okay, so which one of these two chair conformations is more stable? And these are both trans, 1,2-dimethylcyclohexane. Is it the diaxial form or is it the diequatorial form? Okay, so think about that. If this was an exam question, I don't know, like the upcoming final exam, and I said, which one of these two is more stable? Which one would you choose? Okay, now let's go back to our model. Let's go ahead and I'm going to go ahead and save this, and I'm going to close it out. So let's go ahead and now draw diaxial and diequatorial 1,2-dimethylcyclohexane. So I'm going to build. I want a ring. I want a cyclohexane ring. So the first molecule I'm going to build with my cyclohexane ring, and this is where honestly the tubes come to be really useful. If I want to make the diaxial dimethyl, I'm going to hit my methyl group and I'm going to put one here and I'm going to put one there, so that hopefully you see that I have made those two methyl groups now diaxial. Okay, so that's molecule number 1. Because I can do this, let's build a new molecule. Let's go back to the cyclohexane ring. Let me go back to my tubes mode because I like to draw it that way. And now let's go ahead and make the diequatorial. So methyl group, diequatorial. Okay, so you can see that those two methyl groups are now diequatorial. All right, so now let's go ahead and go to the setup. Let's set up the calculations. We're going to do equilibrium geometries for both, calculate what the most stable equilibrium geometry is, the minimum energy, and we're going to do that at semi-empirical levels. And I'm going to go ahead and say submit, and I'm going to call this dimethylcyclohexane, and it's going to go ahead and do those two molecules, and it's done. Okay, so here's molecule number 1, diaxial. Here's molecule number 2, diequatorial. Let's get a spreadsheet out and let's figure out which one is more or less stable. So molecule 1 is diaxial and the molecule 2 is diequatorial, and it's kind of hard to see, but diequatorial. Okay, let's go ahead and say give me the relative energy, and boom. Now, which one has the higher energy? The higher energy is the diaxial by 6 kilojoules per mole over the diequatorial. So hopefully you got that question right. The diequatorial is more stable because it is a lower energy. So we could go back to our slide and we can say, okay, what was that? That was like it was like 6.95. So in other words, for the diaxial, it was 6.95 kilojoules per mole, and the diequatorial, and that methyl group shouldn't be there. In the diequatorial, it was 0 kilojoules per mole. So which one has the lower energy? That one. Oh, I think that's a question in the report form, so everybody should get that right. But that's as much as I'm going to give you. So now that we have those energies, can you calculate then the percentage of equatorial and the percentage of diaxial using this chart. And also in that lab report or in the report format, and you're going to answer these questions online, but you have a printed out copy here. So question number 1, which one is more stable, diaxial, diequatorial? Everybody should get that one right. Question number 2, given the energies that I just wrote down from the video presentation, what in the chart, what would be the percentage of diequatorial and diaxial? Provide a brief explanation of why the most stable conformation is the most stable conformation. And again, well, not again, your explanation can be something stabilizing for one or something destabilizing for the other. Then there's an open-ended question here about when you calculate those percentages, what did you think? Did you think that number would be higher, would be lower? What did you initially think about that? Just kind of getting a feel for, oh wait, that's a lot bigger or that's a lot smaller than I would have predicted. If I was really smart, I would have made the tape stop and have you enter in your percentages. So that's going to be the questions you're going to answer for the case study number. It's 4 on the video, but it's number 1 in your report. All right, let's go to case study number 5, which is going to be number 2. Let's talk about the stability of carbocations. Something again from first semester organic. And in this case, what I'd like to do is how much more stable is primary, secondary, or tertiary? Which one is the most stable and by how much? All right, again, if you've made it this far, you should be able to tell me which one is the most stable and which one is the least stable. Now, in addition to these two, we're going to do a couple of other carbocations. And these ones we're going to kind of have to do on our own. The reason that these all have 4 is because if you're going to compare energies, you have to have the same molecular formula. So the minute I do the following, and you know what? Just for the sake of argument, let's do this. Okay, so these are going to be different groups. I'm going to do them all at once, but I'm only going to compare these 3, and then I'm going to compare these 3. Now, for these carbocations, which one should be the most stable? Which one should be the least stable? We can do a very rough comparison of this one to this one. Right? Because in lecture we say, well, okay, this is a primary carbocation, right? But this is a primary allylic carbocation. This is a flat-out primary carbocation. How much more stable is the primary allylic versus the primary? So we can get a general idea in terms of kilocalories or kilojoules per mole, how much more stable it is. So all I have to do is draw these 6 structures, do the calculation, and then we'll get the energies for these. And so I'll put those energies, we'll put those on the slide. So let's come back to it. So now let's go over here. Let's go ahead and say, let's save. And let's close it out. Now let's draw carbocations, which should be relatively straightforward. Butane, 1, 2, 3, 4. Let's make it a primary carbocation. To do that, I need an eraser button to get rid of the third bond. So now I have what will become a primary carbocation. All right, new molecule. Let's make the secondary. So carbon, 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 our butane, and now let's erase that. So now I've got my secondary carbocation. Okay, new molecule. Let's make a tertiary carbocation, but now what I'm going to do is this. Now I'm going to bond 1, 2, 3. I'm going to make my tertiary carbocation, but now what I'm going to do is now I'm going to erase that. So now there's my tertiary carbocation. And since I'm going to just do all the calculation, now let's do the three allylics. So build a new molecule. Let's go with a double bond. So here's my carbon-carbon double bond. Now I need an sp3. So let's go here, and now let's erase. So there is my allylic, or actually it's my non-allylic carbocation, because the carbocation will be primary, but there's no double bond next to it. Great. Next molecule, let's draw the allylic primary. So I'm going to go with another double bond, but now what I'm going to do is put my methyl group here and put my methyl group there, and now I'm going to go ahead and erase that hydrogen. So now I've got my allylic primary carbocation. And then just for the sake of fun, we'll go ahead and do the allylic secondary. So I'm going to go ahead and put my methyl group here and my methyl group here, and now let's make that a secondary carbocation like so. So I have 6 molecules loaded up here: primary, secondary, tertiary carbocations of butane, primary non-allylic, primary allylic, secondary allylic. So that's the beauty of this, is I can load up these 6 molecules, and now I'm going to go ahead and run the calculations. So I'm going to do equilibrium geometries for each with semi-empirical, which will do carbocations, but here's the thing. This will crash the program. It's not a neutral molecule. It is a +1 cation. So now I'm going to go ahead, let's do those calculations. So these are the carbocations, and now the calculation started. And now we wait. Whoa, 6 calculations later, there they are. Okay, so let's start back at the beginning. So calculation number 1, I'm going to pull out a piece of paper so that I can go back in and write my energies into the slide so that you can use it once I find a pen. Okay, so let's take a look at this one. This is the primary carbocation. Notice that in the primary carbocation, it's sp2 hybridized, like it should be. So for the primary carbocation, what's its energy? Okay, let's use another spreadsheet, and now let's go ahead and let's do the relative energies. All right, so there's my relative energies, and I could sort these, but then it's gonna change everything. So this primary carbocation of butane is 0 kilojoules per mole. Molecule number 2 is the secondary carbocation. It is minus 72.07. 72.07 kilojoules is quite a bit of energy. that's probably enough that if you put, 72 kilojoules of energy into, well, if you put 72 kilojoules of energy into like 100 grams of water, it would raise, I think, by a degree or something like that. So that's a significant amount of energy. Notice it's negative. What does that mean? All right, let's go to number 3. Number 3 was a tertiary carbocation. Again, flat sp2 hybridized carbon. It's minus 122.40. So what's the trend? Again, what does it mean that these numbers are growing more negative? All right, great. Now, first of all, I can't necessarily directly compare the primary non-allylic system to the butane primary carbocation because these do not have the same molecular formula. So when I say that now the primary non-allylic one is at 124.94 kilojoules per mole, well, it's positive. It's very positive. So very unstable. But now let's look at the relative measure. This was the primary allylic system. It's down to 16.39 kilojoules per mole. That's interesting. Is that more or less stable than the primary carbocation that was not allylic? But here's something I don't necessarily know that I would have predicted, which is interesting. Yeah, it's, you know what, it's actually not that interesting. I think I might have another question for you. This secondary allylic carbocation, interesting. It has the same exact energy as the primary allylic. Coincidence? I think not. And I think there's going to be a question on the report form. Why would they be exactly the same energy? Interesting. So we can analyze. Certainly I would take away from that again, primary non-allylic, significantly different than primary allylic. Even, to be honest with you, even with this, the primary non-allylic, the problem here is that the primary allylic and the primary non-allylic, they have different energies, so that means I can't really compare. So I'd have to think of a better example, which I'm not going to do right now. So I'm going to go back to my slide here, and we're going to go ahead and write in those numbers so that you have them to answer the questions on the short lab report. What just happened? Oh, that was the last slide. Why was it the last slide? Okay, so primary was, according to my chart, that was 0 kilojoules per mole. Secondary was minus 72.07 kilojoules per mole. I hate it when that happens. Tertiary was minus 122.40 kilojoules per mole. Primary non-allylic 124.94 kilojoules per mole. Primary allylic and secondary allylic were both 16.39 kilojoules per mole. Okay, so you're going to use those numbers to answer the questions on the lab report. Okay, all right. Case study number 3. Case study number 3 is bromonium ions. This is the last case study, but I think it's one of the more interesting ones. Again, back in first semester, we took a double bond, we reacted it with a bromine molecule. We had the pair of electrons go to the bromine, have the bromine minus leave. So in essence, what I'm adding to this double bond is a Br+. Now, if I do this reaction with adding the Br+ and then adding water, the water molecule in the bromonium ion, right, because we have this bromonium ion, we have a delta positive charge here, we have a delta positive charge there, we have water, and water's going to add to one of these two carbons. In the handout, I'm going to have a slightly different molecule, but let's just say for the sake of argument that I've got a methyl group here, I've got a hydrogen here, I've got a methyl group here, a hydrogen there, and then over here I have my hydrogens and I have my methyl groups. So we're going to do this calculation, and then I'm going to make it unsymmetrical by basically moving this methyl group over to this side. Okay, but let's do a symmetrical one. So what I'd like to do is I'd like to model this bromonium ion intermediate with the triangle. Now, my question would be, and it's not a question for the online report, which carbon is the water going to attack? And if you said either A or B, you're correct because it's symmetrical. Great. So let's go ahead and let's do that calculation. Now it's going to require some trickery here to draw the bromonium ion. So I'm going to go ahead and save those carbocations, which turned out to be much more interesting than I thought. And now let's see about trickery in terms of drawing the bromonium ion. Now, and I know exactly how I want to draw the bromonium ion. I need a ring. You know what kind of ring I need? I need a cyclopropane ring. There's my cyclopropane ring. And the beauty of this is I can click bromine. What? What? I guess I don't have that much trickery. Stop. Let's see if it'll do it now. No. You're aggravating me. I can make this happen. Let's go to the inorganic mode. Because normally bromine only has one bond. Let's choose a bromine. But now let's make the bromine have two bonds. Now let's go back and see if it will let me do this. Ah, beautiful. So I can mutate things by simply making sure that the number of bonds matches up. Again, with this inorganic mode, I could have the bromine have 7 bonds. So I just made my bromonium ion, except now what I've got to do is go back here, and I've got to put a methyl group there, a methyl group on this side, and then the hydrogens go there. Right? So I just made bromonium ion number 1, which is symmetrical. It's the one I drew here. But now what I'm really interested in is making it unsymmetrical. So making it unsymmetrical, I'm going to look at my handout here, and I'm going to do case number 3, which is I'm going to have 2 methyl groups on one side, and I'm going to have another methyl group on the other side. It's far more interesting to get rid of this methyl group and make it a hydrogen. And let's go ahead and do that. So I'll modify this so that I'll just put an H there. So let's go ahead and do that one. Although, to be honest with you, we could do all three. So, you know what? Let's do all three. Let's do a new build, and let's pull up another three-membered ring. Let's pull up another bromine and replace those, and then erase each one of those extra bonds. And now let's go ahead and put the methyl group in here. Oops. Oh, wrong thing. Undo. Methyl group. Let's put a methyl group here. Let's put a methyl group here. And let's leave two hydrogens on that side. So let's make it unsymmetrical and see what happens. So that's going to ultimately be the molecule that we look at. But just for the sake of argument, let's go ahead and do a new build. And let's go ahead and use another cyclopropane molecule. Change the bromine over again. Nope, don't add it, but change it. You have to hit the eraser button every time you want to erase something. Now I'm going to go back here to my organic mode. Now let's put methyl group, methyl group, methyl group. So now it's unsymmetrical that way. All right, so I have three different arrangements of the bromonium ion. Perfectly symmetrical, one methyl group on a side, and then unsymmetrical, two methyl groups and no methyl groups, or two methyl groups and one methyl group. Let's go ahead and set up the calculation. So the calculation is going to be to do equilibrium geometries for each one of these at the semi-empirical level. And again, I'm dealing with carbocations, so I need to make sure that they're all carbocations. Now I'm going to submit it. I'm going to call this the bromonium ion. Bromonium ions. And it's going to go ahead and do the calculation. Now it may complete really quickly. Okay. So here is the symmetrical one. Nope. Where is the symmetrical one? I lost the symmetrical one? Well, that's unfortunate. So let's build a new molecule out of this. So do I have three? Let's just do one more here. I screwed that up. Again, if this is a professional operation, I would go back and edit that part out. And I still may. But you would never know because you wouldn't see the edited part. So now let's go ahead and put in the symmetrical one. There we go. So I have 1, 2, 3. So I've got my three molecules, two methyl groups on a side, two methyl groups on one side, another methyl group, and then the symmetrical one. I'm going to go ahead and redo the calculation here, which isn't a big deal because it's really going to just look at the last one. And so now it's done. So now I've got the symmetrical one. Okay, so here is the symmetrical. Here's the symmetrical bromonium ion. What do you notice about its structure? Where does the bromine sit relative to the two carbons for the symmetrical one? Now, what about when I have, let me reorient this. How about when I have two methyl groups on one side and one methyl group on the other? What do you notice about that structure? The reason that I'm kind of rotating around like this slowly is because you will want to take a look at this, and you may need to replay this part of the video, because what I'm going to ask you to do is I'm going to ask you to tell me what does the geometry of, and let me put this into, to make it a little bit clearer, let me put it into a tube mode. What does the hybridization of this carbon right here with the 2 methyl groups look like versus the hybridization of the carbon with just 1 methyl group? So if you look at that, what would you say those geometries are as I rotate around this molecule? Okay. And let me go back. This was the symmetrical one. So as you look at the symmetrical one, as I rotate it, what does it look like the hybridization of those carbons attached to the bromine? What does it look like they are? Okay. So there was 1 methyl group, and here is 2 methyl groups. What does the hybridization of those carbons look like? What about the position of the bromine relative to those 2 carbons? Which one is it closer to? Which one is it farther away from? Okay. And now let's go to the one that had 2 methyl groups and 2 hydrogens. Let's see what it looks like. Just do one more flip, and there it is. So now look at it as I rotate it. What's the hybridization of the carbon with the 2 methyl groups? What does the hybridization of the carbon with the 2 hydrogens look like? Which one is the bromine closer to? The carbon with the 2 hydrogens, or the carbon that is close, or is it closer to the bromine with the 2 methyl, or sorry, is the bromine closer to the carbon with the 2 methyl groups? What are those geometries? This is, we did not draw bromonium ions like that in lecture. But that is probably closer to what the true structure really looked like. So my question then is, we have 3 geometries here of 3 different bromonium ions. One where there's 2 methyls, 2 methyls versus 2 hydrogens, 1 methyl, so it's symmetrical, and then 2 methyls and 1 methyl. And this sort of unsymmetrical triangle exists when the groups are different on the 2 carbons. And so I'll lead you through a series of questions that I want you to answer about that. But first of all, see the fact that there is still a triangle. So when the water comes in, how does the water have to add? The water has to add from underneath, right? We know that when we were doing this bromonium water addition, that the bromine, we added a bromine, an OH, 100% trans. Now what I'd like you to think about is, how about the regioselectivity of this? Where does the bromine end up? On the carbon with the most hydrogens, or the carbon that's most substituted? Why? How does this geometry or this geometry how does that support what we know to be the correct regioselectivity of this reaction? And regioselectivity meaning Br plus is the electrophile. This is Markovnikov addition. So how does this relate to that? We know the water is going to add from underneath. Where's the water going to add? Is it going to add to the carbon on the right? Is it going to add to the carbon on the left? Why? Symmetrical one is pretty boring at this point. Because since it's symmetrical, the water is going to add 50% to one, 50% to the other. Not so for the other geometries. So I'll lead you through some of the questions. You may have to come back and just focus on the last 5 minutes or so and maybe watch me rotate the molecule around. But how does this relate to the regioselectivity of bromine and water addition to a double bond? It clearly shows that the triangle is intact, so the water has to add from underneath. Clearly it says that has to be a trans addition, which is the stereoselectivity. Okay, so if you're, this is kind of a review, getting you in the mode for review, but also what I hope I've shown you is that we can use these calculations. And I'm doing this not with a $5,000 computer. I'm doing this with like a $699 Micro Center computer. Okay, the software is $1,600. But right now, if I wanted to buy it, I could buy it for $400, which I may do by summertime, just to have another copy, dirt cheap. But we can ask some of the questions about these reactions. And these computer calculations will help us be able to answer some of those questions. And we can also model biomolecules, and that is really helpful if we want to look at potential drug molecules for any kind of biomolecule. And so when I first saw this, I guess it made more of an impact on me than I ever thought, when I just saw this lonely little $1 million computer that didn't have the computational power that I have now in the basement, and they were doing modeling on these biocides and herbicides, trying to figure out how to prevent, disease in crops. This whole area has moved to something that is absolutely critical to be able to do drug design. And where there are supercomputers in the U.S. government right now, a lot of computational power is being thrown at trying to figure out what kinds of receptors and what kind of drugs would fit into those for what we know about the coronavirus proteases. So that's, again, ripped from the headlines and the whole reason why you're watching this. So hopefully you found this interesting, not too boring. If hopefully you didn't sit there and watch this the entire time, you maybe broke it up into sizable pieces. You're going to turn in an online lab report answering the questions from the handout. And if you have any questions, put them on Piazza. Set up a Zoom meeting. This report, the online report, will be due, and there'll be an announcement in the Canvas site telling you when the report is due. Okay, so that is it. Oh my, an hour and 20 minutes. Hopefully you broke that up.